quantum computing, like many other emerging technologies, has been both overhyped and underappreciated. For the students of there in particular, I think it might be an interesting topic because as the rising generation of data scientists, their careers will evolve and grow as quantum computing evolves and grows. And so my aim today is to give you a bit of an idea of how quantum computing works and what to expect from it. And how can we participate in the future co-evolution of quantum computing and data science? Now, quantum computing is a vast topic. So I tried today to balance, I will try to balance, kind of giving you a general overview of quantum computing and also giving you some concrete examples to give you a flavor of how quantum computers deliver their computational advantage, or I should say, expected to deliver the computational advantage, because first practical applications are expected in a few years. The talk today is going to consist of two parts primarily. The first part is introduction to quantum computing, is the biggest part. I'll talk about why would statisticians and data scientists be interested in the topic. Then I'll talk about quantum physics because it is what quantum computers harness as a computational resource. I'll talk a bit about what makes quantum computers powerful, give some examples, and then talk about the current state of quantum computing hardware. Then the second part, the smaller part of the talk, I'll talk about quantum algorithms, what kind of quantum algorithms exist today, and then dive into one of the examples of quantum approximate optimization algorithm, which is an important algorithm that also is possible to cover in a short period of time in a seminar. And then I will conclude. So quantum computers, they exploit quantum physics as a computational resource, and they behave fundamentally differently from classical computers. Classical computers, as they were as they emerged and reached maturity, transformed statistics and data science. And so one can expect that the evolution and maturation of quantum computers will also spawn a new evolutionary branch of data science, just like classical computers did. If you consider modern statistical methods that we use today, from multivariate analysis to iterative methods, to resampling, to practical Bayesian statistics, to simulation, Markov chain Monte Carlo, neural networks, graphical models, so on, all of these methods actually co-evolved with classical computers. They all emerged because classical computers became available. We all know and think of, we can easily list some of the properties of classical computers, such as stable and very inexpensive memory, extremely high fidelity logic gates, high processing speed compared to the previous, mechanical computers or just doing things by hand as people used to do. But there's some fundamental properties of classical computers that we're so used to that we take it for granted. We think this is how computing is. Like, for example, the ability to copy data. Our computers can do it easily, but it's actually not a given. And a lot of the methods we use, like iterative methods or sampling or whatnot, depend fundamentally on the ability to copy data. Ability to reset individual bits, same thing. It's actually not a given for a computational resource. Or things like irreversible gates like AND and XOR that we use a lot. It helps us in addition and things like that. So a lot of things that we do, and even the way we think about computational problems, is informed and based on the fact that we grew up together with computers as applied mathematicians, statisticians, data scientists, physicists, and so on. So quantum computers are fundamentally different from classical computers. And what makes them different and powerful are the four properties they derive from quantum physics that they harness, which is superposition, entanglement, parallelism, and interference. And I'll talk about what each of these mean in a few minutes. But I'll start first by introducing quantum theory, which is the theory of kind of nature at the atomic scale, right? Nature at the atomic scale behaves very differently from what we're used to, because things that we interact with every day, like a cup of coffee, for example, has about 7 septillion atoms in it, and like a few septillion atoms in it. And so what we see is kind of like for it's not a precise word, but it's like large sample properties of quantum physics. We don't see the small sample properties of it, so we're not used to it. It's quite counterintuitive. But mathematically, quantum theory, which describes this quantum physics at the atomic scale, is probability theory with a two norm. And what I mean by this, I will explain in a second. So classical probability theory, laid out on the left-hand side that we're used to. So we have a system that can have some kind of n events. And these n events, for each of these events, we have an assigned probability from P1 to Pn. And these probabilities have to be real and non-negative, right? And they're normalized to 1 using the so-called 1 norm, meaning that the probability is raised to the first power before it's summed up. So this is the norm, and they all sum up to 1. This is our classical probability. Now, in quantum theory, instead of the events, we have possible states. So we have a quantum system that can exist in one of n states. And instead of probabilities, we assign amplitudes that are related to probabilities in a way I'll talk about in a moment, but they're not the probabilities. So physicists like the Greek letter psi for some reason for quantum mechanics. It's historical. So I'll use psi so you get used to it. If you read quantum computing papers, you'll see a lot of it. So from psi 1 to psi n, these are the amplitudes. The amplitudes can be complex valued. They don't have to be real and non-negative. Then can be negative and more generally complex. And they're normalized to 1 using a 2 norm. So the amplitudes are raised to the second power. So you take the absolute value, you raise the amplitudes to the second power, and then that thing adds up to 1. It's like the Euclidean norm. Right, and so looking at the normalization, you can say, well, maybe these squared amplitudes have something to do with probabilities, and they actually do, and we'll get to that in a moment. But this is the difference between quantum theory and probability theory. That quantum theory, that for some reason we don't know why, but we just know that it does because of experiments, like multiple experiments that have been done over 100 years. We know that for some reason that's how nature behaves at the atomic scale. So in quantum theory actually at the core of it is linear algebra on complex vector spaces, right? It behaves very similarly to the linear algebra that we're used to, except instead of the real valued coordinates, we have complex valued coordinates. So we take these amplitudes. So we have a quantum system that can be in one of the n states with these amplitudes assigned to it, and we make a vector out of the amplitudes so that each state corresponds to one of the directions and the amplitudes form a vector. And this little thing here is called a ket. It's kind of like an arrow. It's like to represent this vector in this vector space over the complex field. It's called a Hilbert space. It's very analogous to Euclidean space that we're used to with the real numbers. So this is just a vector. This ket, the quantum state, is described by a vector in this complex vector space. And for a closed system that can only exist in one of these n states, any transformation of such a closed system would be just a transformation into another vector in the same space. So it's a linear transformation from one vector to another. And the linear transformation has to preserve the unit norm. It has to preserve inner product. So that makes it so-called unitary. But the point is that it's linear, that transformations in quantum mechanics are linear. And we have this vector space. And from this simple foundation of this kind of probability theory with a 2 norm in this vector space, we actually derive all these properties that give power to quantum computers: superposition, entanglement, parallelism, and interference. And I will explain each one of them in order, starting with superposition, kind of going clockwise. So the first one is superposition. It's the idea of a quantum system being able to be in several states at once. You may have heard about the Schrodinger's cat that's at once dead or alive and stuff like that. But you don't have to get this spooky, right? It's actually within linear algebra, superposition is a very intuitive concept of just taking this vector in this complex vector space, and just decomposing it as a sum of basis vectors of that space. So each of these E1, E2, En is just a basis vector in this vector space, and we just have a composition of these vectors composing this vector psi. And that's what we mean by superposition. Now, even though it's a simple concept from a linear algebra perspective, it's actually very powerful in computing, as you'll see in a few moments. The idea of superposition is related to quantum measurement. So when we create a quantum state, if we were not the one creating it, or we don't know how it's been created, we actually don't know what's in it. We can't just look at it and say, oh, you know, I can read off all these coordinates. No, it's like a black box. And the only way you can get information out of it as a classical observer is to take a measurement, a quantum measurement, which is like a, you know, measure. You take a physical apparatus and you measure certain things like voltage and current and whatever physically. The quantum measurement is done on a certain basis. And when you measure something, when you measure a quantum state, you get one of the basis states with a probability that's equal to the absolute squared amplitudes. That's one of the postulates of quantum physics. Again, we don't know why that works this way. It's called the Born rule. We discovered that it works this way, and nature seems to be this way. Right? This is not a part of linear algebra. This is a part of quantum theory. So this is quantum measurement. To give you a more concrete example, a single qubit. So a qubit, as you may have heard, is the simplest unit of a quantum computer. It's a quantum analog of the classical bit. Right? The classical bit, which is the simplest unit of a classical computer, can be in one of two states, either 0 or 1. A qubit, the quantum analog, is a two-dimensional quantum system that can be in a superposition of 0 and 1. And you can see how that might be useful in computation. So in a classical computer, if you want to run a code on a bit that's equals 0 and a bit that equals 1, you have to run it twice. Whereas in the quantum computer, you kind of can run the code on both 0 and 1 at the same time if you put this qubit Q in a superposition of 0 and 1. Q0 and Q1 are the amplitudes, right, that are normalized to 1. So Q0 squared, absolute squared, and Q plus Q1 absolute squared equals 1. If we take a quantum measurement of this qubit, then we get either 0 with probability that's equal to the squared amplitude Q0, or we get 1 with a probability that equals to the squared amplitude Q1. So that's how a single qubit, which is the simplest part of a quantum computer, works. Okay. Now, the second property of quantum computers is entanglement. Entanglement is related to superposition. It's the idea that quantum superposition can actually span multiple quantum systems, not just one. So if you look at the entangled state here, so this is a state over 3 qubits, right? We can have a quantum state on 3 qubits. We can say, okay, we'll say that the basis states of this quantum system are all the permutation of the basis states of each single qubit. So for example, this is qubit 1 in 0, qubit 1 in state 0, qubit 2 in state 0, qubit 3 in state 0. This one is qubit 1 in state 0, qubit 2 in state 0, this is qubit 3 in state 1, and so on. Right? So these 0, 0, 1, 0, 1, but for the entangled state, I can't manipulate one qubit at a time without it. Okay, so that's entanglement. The property of quantum computers that quantum computers harness is parallelism. It's kind of a consequence of superposition and entanglement. It's the idea that, again, because we can create an n-dimensional vector on log n qubits, we can manipulate an n-dimensional vector with about log n operations if we use single qubit or kind of 2 qubit, 3 qubit operations. Right, so we can do things in parallel in a way, and I'll give you an example of how that works in a moment. The last property is interference. That's kind of the strangest property there. It's the property that quantum amplitudes, unlike probabilities, can cancel out because these quantum amplitudes can be negative or complex number. Right, that's why they can cancel out. And to understand how that works, we'll consider a quantum coin toss, which is a quantum equivalent of a classical coin toss. So in a classical coin toss, what do? We take a coin, starts in heads or tails. We flip it. If it's a fair coin with probability 1/2, it lands either on heads or on tails, right? A quantum coin toss is, in a quantum coin toss, we take a qubit, a two-dimensional quantum state with basis factors 0 and 1, say 0, started in state, initialized either to 0 to 1, and then we flip it. But we have to use the rules of quantum mechanics to flip it. We have to have a linear unitary transformation. And so we find the transformation, such as the end probabilities of us after this quantum coin toss. If we measure the resulting qubit, we want to get 1 with probability 1/2 and 0 with probability 1/2. And so this kind of transformation is both unitary and gives us what we want, these equal probabilities of measuring 0 and 1. So when we applied this transformation to the quantum state in initialized to 0, we get a superposition like this of 0 and 1, right? That's the coin toss. If we apply it to 1, we get a very similar superposition, but it has to have a minus sign here because of unitarity, because it has to preserve the norm and it has to preserve the inner products. And but if we measure these 1 and 0 and 1, we get 0 with probability 1/2 and 1 with probability 1/2, just like we want. Now, the fun stuff starts when we do the second toss. Now, let's consider the classical case first. So we take a coin, it starts, let's say, in heads, like on the left. We toss it, it lands either on heads or tails with probability 1/2. Now, after it lands, we can toss it again, and it lands again on heads or tails. And let's see what's the probability of it landing at the end of this process on, say, tails, right? So in order for it to end on tails, first, it can either land on heads with probability 1/2, and then from there, it lands on tails with a probability of another 1/2. So 1/2 times 1/2, the total probability that the coin goes down this path is 1/4. Or alternatively, first it could land on tails with a probability 1/2, then land on tails again. The total probability of getting tails down this path is 1/2 times 1/2 equals 1/4. The total probability of the coin ending on tails after 2 flips is 1/2. You can do similar analysis for starting with heads, ending with heads, starting with tails, ending with heads, and so on, right? That's the classical coin toss we're familiar with. Now, with quantum coin toss, things get a bit strange. So with the first coin toss, we apply our coin toss operator and get these superposition states. When we apply the second coin toss, this is a bit mathematical, but it's actually, I think, easier to understand. So the first coin toss gives us the top line. If we apply it to, let's say we start with a qubit in the state 0, apply the coin toss, get a superposition of 0 and 1. Then we apply it again to this state. So we're applying the coin toss to this resulting superposition state. This operator is linear, so we can open the brackets and apply the coin toss operator to 0 and 1. Multiply this through, so this equals that, and this equals that, right? We multiply it through, and what do we get? We get the cancellation of 1. So the amplitudes of the outcome 1 cancel out, and we only get outcome 0 with probability 1. And if we start with the state 1, the amplitudes of the state ending state 0 after 2 coin tosses cancel out, but the amplitude of the state 1 gets amplified to 1. And so we can get this kind of behavior from classical probability theory, but this is what quantum theory does. And that's also very important. This interference property is important in the power of quantum computers. So this is where power of quantum computers comes from: superposition, entanglement, parallelism, and interference. To give you a concrete example of how this works, let's consider a the simple search problem. So we have, let's say, the problem is to find the correct 100-bit string Z star, a function that labels the correct string. It finds the correct string. So if the string is correct, then the function gives us outputs 1 If the string is wrong, the function output is 0. 100 bits doesn't sound like a lot, but actually all the combinations of all the strings is 2 to the 100th power strings, which is 10 to the 30th power combinations. And the classical computer has no choice but pretty much checking every single one. And on average, it would have to check half of them, right? Before it gets to the right one. So the classical computer performs order of n operations to find the correct string among the 10 to the 30th power strings. A quantum computer can proceed differently, right? In a quantum computer, we can start by making a uniform superposition of all the strings using 100 qubits. And the state is 2 to the 100th power, a dimensional state, right? Our n is 2 to the 100th power. And we will create it's possible to, fairly straightforwardly, to create a unitary operator that will test each of these strings in parallel and record in an extra qubit the label of the strings. So it will label the wrong strings as 0, so and label the correct string as 1 in this extra qubit that we attach to the system. So the quantum computer uses log n qubits for this problem, using superposition and entanglement, because we can create the superposition state, right, an entangled state over 100 qubits. It uses order of log n operations to label the strings a star. Because of quantum parallelism, you can check each qubit one by one to check whether it's the correct qubit, so 100 operations. Now, if we could stop there, and if we could open the quantum box somehow and say, okay, well, I'll pick out the one labeled 1, then we'd have exponential speed up from the quantum computer. Unfortunately, we can't do that. We have to measure, right? We have to take measurements to extract information from the quantum state. And if we stopped at step 2, then the number of measurements we'd have to take to extract the label string would actually be order n. It's because each one of these strings if you take measurements of this state, then each one of these string has the probability of squared 1 over square root of n, so 1 over n of being the string measured. And so you'll have order n measurements to extract the one that's labeled correctly. Now, luckily, we don't have to do that. We can amplify the string that's been labeled correctly. And a quantum computer can amplify it and order square root n operations. It was a very famous quantum algorithm that was proposed by Love Grover in 1996 called Grover search, where Grover proposed a way to amplify the correct string and also proved that order of square root n quantum operations is the optimal complexity, the optimal number of operations at which a quantum computer can perform this task. This amplification can be done only because of interference. So the search problem can give quadratic speed up over a classical computer because of superposition and entanglement, because of parallelism, and because of interference. Right? In general, a general quantum algorithm, so I showed you one quantum algorithm. The general quantum algorithm consists of 3 parts. One is quantum state preparation. Now, in Grover's algorithm, the initial state preparation was quite easy. You had to create a uniform superposition of n strings, and that's pretty straightforward in a quantum computer. Things may not be straightforward if you need to record some classical data, if there's a lot of classical data. So this can be actually quite a resource-consuming task and something to think about when creating a quantum algorithm. The second part is the actual quantum computation. And the quantum computation is just a linear transformation of the input quantum state into the output quantum state, right? All quantum transformations are linear. And so that's what the quantum algorithm really is, a linear transformation using individual qubit or 2-qubit, 3-qubit gates. And the last step is the post-processing and readout. Like in the Grover algorithm, it was the amplification of the correctly labeled string, and then the readout of that string. So oftentimes you need to use interference and so on to amplify the correct result and to dampen kind of the garbage calculations, the incorrect results, and then read out the result into the classical computer, because at this stage, both humans, humans make decisions based on classical data. Quantum algorithms are actually quite challenging to write because quantum computation is quirky. You have these powerful things like superposition, entanglement, parallelism, and interference, but you also have some quirks. Like, for example, in the quantum computer, you cannot copy unknown states. So if it's not a simple basis state and you have a result of computation, you can't copy it several times. Like if you have a result of computation and you have to measure it many, many times to extract the data out of it, it would have been nice to be able to just copy it and then measure each one, but you can't. You have to recalculate each time you want to take a measurement. So that limits the power of quantum computers. Secondly, you cannot erase or discard intermediate results. Like we cannot just reset all the bits to zero like we do in a classical computer. You have to uncompute to reset your qubits carefully. Third, quantum operations are linear, and that also limits what we can do. Now you can make nonlinear operations, create effectively nonlinear operations, but this comes at the expense of using extra qubits, so extra space on the quantum computer. And lastly, quantum computation, because it's linear, it's reversible. And we're used to a lot of irreversible thinking like and and XOR. And even though classical computation can't be reversible, this is not what we used on day-to-day basis. So it's another layer of kind of quirkiness when you think about quantum algorithms. So on one hand, quantum computers have these 4 powers. On the other hand, they're really quirky. And how do we know they actually deliver at the end of the day? Well, we know courtesy of theoretical computer scientists. Theoretical computer scientists study problems in general. They study the computational complexity of classes of problems, and they see how hard problems become for a certain type of computation when the input size becomes, for example, very large. Right? How much memory space does the problem need? How many operations at the minimum does the computer have to perform in order to solve the problem as it grows large? Computer scientists have many complexity classes for various classes of problems. I pointed out some kind of the simplest ones that are related to quantum computations. Now, the easy problems for classical computers are called the complexity class P. These are the problems where the resources a classical computer needs to use scale polynomially with the input size, right? And it's a small subset of things that the classical computers do easily. BPP is the next kind of class, the next easiest class for classical computers, where these are hard problems for classical computers, but they can be made relatively easy by using randomized algorithms. Now, the complexity class for quantum computers is BQP. So BQP is the complexity class of problems that are easy for a quantum computer. And you can see that the class of randomized algorithms are actually quite a bit smaller than the class of problems that are solved by computer algorithms. So you can't de-randomize all problems that are solvable by a quantum computer. Anyway, the typical hard problems, oftentimes we work at in, say, business analytics, are the NP hard problems. They're problems of optimization, problems of finding a minima on a kind of non-uniform landscape and so forth. These are NP hard problems. They're hard for a classical computer. They scale exponentially. So as the size of the problem, as the size of the inputs grows, the amount of resources a classical computer needs to use grows exponentially. The good thing is that once you have the correct result, for NP hard problems, it's pretty easy to check it. It takes a polynomial time to check it. So for example, finding the correct string is an NP hard problem. There's a subclass of NP hard problems that's called NP complete. These are the hard problems in an NP class, but if you unlock one of these problems, you can solve all of these NP hard problems. Theoretical computer scientists have shown that quantum computers cannot solve NP complete problems. So unfortunately, we do not have a magic bullet to solve all NP hard problems. We can solve some NP-hard problems, most likely, with a quantum computer. And actually, we know that we can. There are some problems that have been demonstrated to be NP-hard and solvable by quantum computer. But we cannot solve the NP-complete problems. Now, there are also problems that are even harder than NP-hard. So these are problems that take exponential time, and you can't even check whether the solution is correct if you're given one in polynomial time. So it's really, really bad. And there are other classes of complex problems. I've simplified this chart tremendously. But the point is that the complexity class of problems that are easy for a quantum computer includes some problems that are harder than NP-hard. So quantum computers can definitely deliver some really good stuff for us, and we know it from our theoretical computer scientists, among other proofs. But from a practical perspective, it's not just quirky theoretical computer science problems. Sometimes the theoretical computer scientists can concoct very impractical problems to test computer power. But no, actually, quantum computers have wide-ranging practical applications that are truly transformational, just like classical computers were, say, 100 years ago, not 100, less than 100 years ago. They transformed the last half a century or more. And the first type of quantum algorithms are the quantum simulation algorithms that can enable molecular engineering, so engineering of pharmaceuticals and fertilizers and energy solutions at a molecular level. Materials discovery, protein folding, that's very important in medicine like Alzheimer's and Parkinson's and so on, and so forth. And this has dramatic ramifications for very important sectors of the economy. The second part is cryptography, and this is why a lot of governments are investing a lot into quantum computers, because actually the first practical application of quantum computers that started this all as quantum computers as a realistic computing machine was Shor's algorithm for breaking public key cryptography. Public key cryptography is what we use today pretty much to secure all of our transactions, from national security to financial transactions to everything. Now, there are other ways to do cryptography, but it would cost a lot to change it all. And so governments don't want to be the second, governments of individual countries don't want to be the second government to get a quantum computer. They want to be the first, all right, because of this issue. Then there are on the positive side, you can have unconditionally secure cryptography and so on that's based on properties of quantum mechanics that actually makes kind of unbreakable cryptography that could be good. And so that's another application. Now, of interest to us as data scientists and statisticians is kind of quantum computation, doing computing tasks with classical data, and things like fast linear algebra, optimization, quantum Monte Carlo, Markov chain Monte Carlo, quantum search and statistics, true randomness, and quantum machine learning models. And of course, all these things have applications wherever data science has applications. So everywhere, finance, healthcare, logistics, transportation, processing industries, and so forth. And so when can we expect all these goods? When can quantum computers actually deliver something practical? And the answer, according to at least IBM, is that quite soon. IBM right now is the top provider of quantum computing hardware. They have cloud access. They provide cloud access, both free cloud access to academics and premium cloud access for people who want to run high fidelity algorithms to multiple machines, quantum computing machines. Right now, their biggest machine has 127 qubits, but soon it should grow to about 433 qubits. This is their development roadmap that they publicly publish. And so we're in this interesting point right now in 2022, where we're after quantum supremacy has been demonstrated by Google. So quantum supremacy is when a quantum computer was able to perform a task that a classical computer would take a lot longer to perform. Like their quantum computer performed something in a couple of minutes that would take several days for the most powerful classical computer to perform. And so even though at the time when Google announced quantum supremacy, it was a bit controversial, IBM came out and said, oh, this is not quantum supremacy, you're exaggerating. Actually, this result stood at the end. At the end, there is a consensus that Google actually did demonstrate quantum supremacy, except it was not on a practical task. It was on something that's a toy model. Well, IBM expects real-world applications by 2025. And so far, they've been pretty decent at meeting their milestones. So we shall see. But this is, this is only a couple of years. And it's surprising, but that's what they say. So we will watch the space. Now, there are some serious hardware challenges for IBM and others like IonQ and Honeywell and other builders of quantum computers to overcome. And there's qubit connectivity. So making qubits, particularly those that are far apart, have a quantum entangled connection to each other. That's hard. Decoherence is just like maintaining the quantumness for a sufficiently long period of time that you can perform a calculation. And then noise and decoherence noise, and also just when you apply a gate, when you try to control a qubit, that the qubit actually does what you want it to do. And those things are hard to do, and people are working on it. But the technology is improving. So this is from IBM. In 2019, their best machine had 27 qubits. Now it's 127 qubits, where they're pretty optimistic. They think there's going to be 4,000 qubits in 2025, but it depends on one technology of taking these kind of quantum computers and wiring them together. Once you can put two together, you can put more together, and that way you make a 4,000 qubit quantum computer. Fidelity, that's lack of noise. In 2019, the best machines had 99%, although most machines had more like 97%. Right now, the best machines have 99.9% fidelity. IBM is hoping for 99.99% by 2025. And it's actually in the last 10 years, they did achieve a 1,000-fold improvement. So it's kind of on the same exponential line. And again, the coherence times, you can expect them in milliseconds by 2025. And again, that would support a lot of computation. Decent period, but if you think about what happened to classical computers after the first demonstration of a practical application. In 1945, for example, this is ENIAC, the first programmable general purpose computer. The purpose of this computer was to do artillery calculations. And you can see how it was programmed. So these ladies are programming the computer by putting these giant cables between vacuum tubes, and each vacuum tube was it wasn't a bit-based computer, but it was like a bit, and each vacuum tube was a macroscopic thing this big. So after this kind of computer was built, technology there was an evolutionary explosion of classical computing technology. So this is this ENIAC that I just showed you. And in the next 15 years, so 1950, 1955, 1960, you have all this proliferation of all sorts of classical computing technologies. And you can see the evolution of hardware. So these are vacuum tubes from ENIAC. And as I said, so each vacuum tube is sort of like a bit. It's amazing, right? Now we pack billions of them on a tiny little chip. And then in 15 years, this is still the old school, so the vacuum tube technology, not semiconductor technology, but it already looks kind of more modern, like a motherboard. And this is, if history is a guide, that's what we might kind of expect from quantum computers. Now, the biggest thing right now is hardware, right? So the hardware designers need to get to the point where we can have this first application. Hopefully it's not going to be artillery trajectories, but something peaceful. But once we get there are lots of algorithms that we can use that already exist. And of course, once we get to the first practical applications, new applications will emerge. So among the algorithms that already exist, we have fast linear algebra, quantum sampling, quantum neural networks, quantum search, quantum optimization. And I don't want to go through, of course, every single one. I will just do a deep dive. It's 447. So I will just talk briefly about the quantum approximate optimization algorithm, because it's kind of a simple example of a practical algorithm. I'm going to skip over that. It's just the idea is that you can reparameterize the qubit, kind of to consider it like a vector in a sphere. And so think of qubit manipulations as rotations of this vector in a sphere. That's all we need to know. So quantum approximate optimization algorithm gives an approximate answer to a combinatorial optimization problem. Combinatorial optimization is NP hard. Again, you have n-bit strings. Now, quantum computers don't have to work just with n-bit strings. It's just these examples are simple and kind of simpler to understand in a short talk. So that's why I'm using them. So we want to consider all n-bit strings, and we can choose the one that satisfies some kind of M clauses. So we have some kind of cost function that tests each string and sees if it satisfies each clause. And if the string satisfies the clause, then the cost function is 1. Otherwise, it gives out 0. And we have M clauses, and the sum of all the clauses gives the overall cost function. And the string Z star that we're seeking maximizes the cost function. All right, this is the NP hard problem. So the way quantum approximate optimization algorithm works is actually quite interesting. It uses both a classical and a quantum computer. It's a hybrid approach of quantum classical. It's a hybrid quantum classical variational method that's suitable for these so-called NISQS, noisy intermediate scale quantum computers, the ones that are available today. And so what happens is that you start with a uniform superposition state, like we did in the quantum search. So each one of these is a string of 1s and 0s. It's a uniform superposition. And then you apply these individual qubit gates, these rotation gates, to this state S. And you first apply this kind of gate that has a parameter gamma to it, and it kind of applies a complex phase that encodes the information from the cost function with some kind of parameter gamma. And then the second gate rotates the state around the x-axis, each qubit around in the x-axis, using a parameter beta. All right, and you repeat these. So UC, UB, UC, UB, and so forth, p times. So p is another parameter. So you have this parameterized state with vectors gamma, variational parameters, vector gamma, vector beta, and p. And then you measure all qubits, and you measure them, say, m times. You repeat this process, step 1, step 3, m times, and you get, each time you measure all qubits, you get a string of numbers 0, 1, 1, 0, 0, 1, and so on. And you collect these strings, and then you put them in the classical computer collects them for you because you've measured now. So the next step is on a classical computer. You evaluate the cost function because it's pretty cheap. These are short strings. You evaluate the average cost function for the strings you've measured. And based on the value of the cost function, you adjust your variational parameters in the usual way using either gradient descent or Neldermead or whatnot. And then you use these variational parameters and you stick them in the next iteration, and you make another variational quantum state. And the interesting, look, it's beyond the scope of this talk to prove why this works, but Farhi, Goldstone, and Goodman, who came up with this algorithm, demonstrated that in the limit of p goes to infinity, so if you apply these gates infinitely many times, it actually gives out the exact result. When p is not infinity, when p is finite, you get an approximate result, and you can control your approximation by seeing how deep your quantum algorithm is, how many times you have to apply a quantum gate. So if you have a very noisy machine with low coherence, you just use a small p. If you have a nice machine with long coherence time, when quantumness stays for a long time, well, you can apply lots and gates and get an almost exact result. So it's a very nice algorithm that way. So to conclude, if you got interested in quantum computing based on this talk, but want to learn more, here's the time for a shameless plug. Our colleague from there, Min-Nok Tran, and I, together with Scott Sisson from UNSW, wrote an introduction to quantum computing for statisticians and data scientists that goes into more detail about what I talked about. There's an extended version of it online that kind of lays out in fairly simple terms all the key algorithms that can be of interest of statisticians and data scientists. It talks about quantum theory a bit more, kind of gives you, and how to program quantum computers and so on, gives you a foundation of what you need to know if you're a data scientist interested in quantum computers. The second source is Qiskit. Now, Qiskit is actually a software development kit by IBM that you can use. So it's a Python-based software development kit that IBM uses to give people control over its quantum computers. So if you want to run an actual quantum algorithm on an actual quantum computer, you sign up for an IBM account, you go to Qiskit, they have I think a really nice textbook, although some people complain that only physicists can read it. I'm a physicist, so I can't tell. So, but it is a good textbook and it has a lot of examples, and you can run the examples and create something else and run it on an actual quantum computer, which is exciting. Now, if you like things contemporary and sort of gamified and like Duolingo, then there's Black Opal, which is Duolingo of quantum computing. And I have to say here that I have a conflict of interest with this company because I'm sort of a related party and stand to benefit from the success of this company, but I can't not talk about it because it's kind of becoming a bit of a gold standard in introductory quantum computing training, and companies from consulting to universities to, I don't know, device manufacturers and so on, who want their employees to understand quantum computing, use it. And of course, there are a lot of individual members too. So anyway, gamification, your thing, Black Opal is an app. There's an app for that. And lastly, there's tons of other resources out there. And I personally like, for machine learning specifically, I like PennyLane. They provide also software development kit, but they also have lovely, in my view, white papers that have nice visualizations and they're easy to understand. So I recommend that, but there are lots of other resources. And that brings me to my conclusions. So quantum computers can dramatically speed up computation, enabling next generation applications. Writing these efficient quantum algorithms is challenging, but the list is growing and will grow. Quantum computers will give rise to a new evolutionary branch of statistics and data science, because they're so different from classical computers that we'll have to start thinking differently, and it will happen eventually. And then quantum computing hardware is expected to deliver practical applications. Well, IBM says in 3 years. I'd say give them a couple more years, but 3 to 5 years, it's a very short time. And credible real-world applications of quantum computation are in demand. So if you have a good idea of how to use quantum computers to solve something important, then there is demand for these kind of applications. And yeah, thank you for your attention.